In this video we'll talk about refraction and reflection with electromagnetic waves, and one of the terms we'll need to understand is called the index of refraction, often shown as lowercase n. And what is it's a ratio? It's the ratio of c, which is the speed of electromagnetic wave in a free space or vacuum, often called the speed of light, because since light is an electromagnetic wave, divided by the speed of this electromagnetic wave in any other media. And we know that the speed of light is the fastest electromagnetic wave can change, and that's when it's in a vacuum, and the speed of any other media is less than that, so therefore the index of refraction has to be greater than or equal to 1. And we can rewrite this equation as to have this velocity in this other media is c over index of refraction, and the greater the index of refraction, the slower this electromagnetic wave goes in that media. And we kind of know that because we call c is 1 over the square root of the permittivity of free space times the permeability of free space, and that's in a vacuum. For any other media, it's 1 over the square root of the permittivity of that in that media times the permeability in that media, and we know that both of these terms are at minimum when they're permeability and permittivity and permeability of free space. So this denominator's at a minimum this. If it gets any larger, then we know the velocity dropped. We also know that this index of refraction depends on the media conditions and the frequency. For example, for water at 20 degrees C, I have a graph here showing as frequency increases, the index of refraction tends to increase. And I've kind of focused here on the visible light spectrum. So with red, the lowest of the frequencies of the visible lights, and violet be the highest frequency of visible light, we can see that the index of refraction slightly climbs from 1.33 to 1.3427. And this is one of the reasons why we see a rainbow and why a prism can break, a prism using refraction can break this into its visible spectrum so you can see it. And also, but then it was like, as I go to gamma rays or something else, this index of refraction tends to get much, much bigger than that. And we'll learn about refraction here, how angles change, and we'll see why the higher the index of refraction, the more the direction changes, the higher the index of refraction. So that's why violet lights change direction more with refraction than a red light does. Now, thinking about some index of refraction numbers, in a vacuum we know it'd be c over c, so they're defined to be 1. In air, at standard temperature and pressures, it's somewhere around 1.0003. Water, depending for visible light, somewhere around 1.33. Visible light somewhere in glass around 1.5. Visible light in a diamond, index of refraction somewhere around 2.42. And now we talked about index of refraction. Let's actually talk about, so we talked about how it affects the speed. We'll talk about what effect it has on refraction. And what we're going to use is Snell's law, which relates the refractions and the angles of the incident ray and the refracted ray. We'll kind of look right here. So I'll have an example. We'll have one media on this side, another media on this side. The green is like, we'll say air, index of refraction 1.003. Here we'll have, for example, a media water, and we'll approximately say it's 1.33 index of refraction. So therefore, water has a higher index of refraction than air. So we know that the speed, right away, we know the speed of the electromagnetic wave in the water is less than that in the air. But how does that affect reflection and refraction? So let's think about reflection first. So I just drew an arbitrary, so I said that I have this electromagnetic wave drawn here as a ray with an incident angle coming towards that boundary. And we know for all angles, whether it be reflection or refraction, we have this boundary here. We always measure angles from the perpendicular normal to that boundary. So I drew a perpendicular line to that. So I'll have the incident ray, and I'll call my incident angle is the angle from that ray to the perpendicular boundary. So that's my incident angle. And we know if we have any reflection, that the incident angle of incidence equals angle of reflection. So therefore, reflected wave would come back like here is shown, where it's that magnitude of that angle is the same as that magnitude of that angle. So that's reflection. Now we could also have some of this energy in this which would transmit through to the second media. which case would have we'd have a refraction take place. If this media and that media have the exact same index of refraction, then this wave will just continue along the exact same straight line. But if the index of refractions are different, then it follows this law. So typically we'll consider, rather than angle of incidence, we'll call it theta 1. It's really the same angle. And taking this equation, we can solve. We know theta 1 and we know n1 and n2. We can solve for theta 2, the refracted angle in this new media, and theta 2 can simply be take this over here in the denominator and take the inverse sine. So inverse sine of n1 sine of theta 1 over n2, and that's valid as long as theta 2 is less than or equal to 90. And if that answer turns out to be greater than 90, then it turns out that none of that none of that energy will be transmitted in there, and all the energy will be reflected. So that's a critical thing to understand. Now that will not happen for this case, because if I go to a higher index refraction in the second media, then this becomes a smaller number, and the angle also becomes smaller. So the angle relative to the normal gets smaller. So every time I'll go from the low index of refraction, high speed media to a lower speed media, higher index of refraction, this angle will get smaller and it will reflect towards the normal. And so I will never have that case. But if I go the opposite, if I go from a low speed to a high speed, or a high index of refraction to a low index of refraction, when this comes out, it'll rather than keep going there, it'll go to a bigger angle, and eventually, but it can't exceed this. If it's more than 90 degrees, then it's all reflected, and so there's no refraction if this angle is greater than 90 degrees. But that's not this case. So now we can see, here's my theta 2. This is my refracted. It's no longer going the same direction here, but refracted to a different angle. And because this index is greater than the index, it went closer to the normal. So now there's more than just this angle. We need to understand what's happening at this interface. So if I kind of zoom up right around and there, and kind of microscopically look at it, that's kind of a picture right here. It's kind of the exact same thing going on. And so I got my air on this side, my water on this side, low index refraction, high index refraction. Here's my theta 1 coming in, and kind of that's there. And what I've kind of drawn is electric field. Remember, electromagnetic wave has an electric field and a magnetic field. So what I've drawn is the electric field. Electric field is this sinusoidal thing, and I've drawn it like in the plane of the board. So therefore, the magnetic field's perpendicular to that. So that's in a plane like this, going in and out, in phase with that. And now using the right-hand rule, I can take E cross B and find the velocity going in this direction. So first we'll consider, in this case, we'll consider what this ray, and we'll consider the refracted ray coming out of it. So what happens to it? We know the angle changes. What else changes? We know the velocity changes, right? Because I'm now going into this media with a higher index of refraction, so the velocity dropped. So therefore, the velocity in this 1, the entering, was greater than the velocity in 2. And since we know velocity of electromagnetic wave is the magnitude of the electric field over the magnitude of the magnetic field, and I know that the velocity dropped, I know the amplitude of the electric field has to drop. So I drew this as a certain amplitude, and I drew the electric field as a smaller amplitude. Now the magnetic field may have grown up here, but for sure the electric field drops in amplitude, because we know this ratio, this value dropped, so therefore the numerator has to drop in amplitude. What else do we know? We know frequency. So this wave, let's consider it's a singular frequency wave that's coming in there, just as I've shown. The frequency is maintained as it goes through a media, so that doesn't change. So frequency in the media 1 is the same as frequency in the media 2. We'll just assume it's this single frequency thing. So that's true. So now we know we also know that velocity equals frequency times wavelength. So if the frequency is the same, but this velocity is dropped, then obviously that wavelength is dropped. So you can kind of see I have a wavelength drawn here, zoomed up, and when I've drawn it here, I've shortened the wavelength because I know it's shorter wavelength and the electric field is a smaller angle. And I've shown now it's coming out at this theta 2. So is that all there is to it? Well, there's one more characteristic, and that's at least one more characteristic, and the one we're going to talk about is phasing. So let's look at this blue wave right here. I do a sine wave starting from 0, and it has a period of 360 degrees. And then I drew a dashed wave right here, which is 180 degrees phase shift from it. So if these two waves interacted, they would cancel each other because wherever is a plus, there's a minus there. So phasing of waves matter as well. And so what happens to phasing of waves when I go refract through a media? Well, it turns out the refracted waves don't change phase at the boundary. So what I kind of drew right here was I'm coming to the boundary, and I'm coming right at that point, and when I kind of hit that boundary, I'm at a peak. I drew it kind of special because I drew it, we're right at this peak, and we're about to start coming down. So instantaneously, it changes amplitude, it changes wavelength, but it maintains the phase. So I kind of drew it here coming through. It's still at that peak, and it just continues going down. So it's not changed angle, but it maintains phase. So refracted waves, when it goes from one media to another, they don't change phase. Okay, but now let's talk about reflected waves. Reflected wave has an if-then kind of or statement. It either can not change phase or it changes phase by exactly 180 degrees depending on the ratio of N1 to N2. So if N2, the media it's going into, has a higher index of reflection than the media that was in N1, so it came to this boundary and some got reflected, and this N2 is greater than N1, then the reflected wave that's coming back here, this reflected, comes back 180 degrees out of phase. If it was reversed and this media had a higher index of refraction than this media, then there would be no phase change. So, but for this example, you can see that I came in there, I'm at this peak right here. When I came in, immediately this reflected wave changes phase, goes from this phase to 180 degrees out of that phase. So it went from the peak to the valley. Or you can think it moved here, it changed 100, it advanced or retarded 180, so it went to there, which is the bottom. And so now it's going to be, you can kind of see I drew it coming up, it's at the peak, and then when it's leaving, immediately it's at the bottom. It changed phase. And now it's going out, and it's out of phase with that. So that we're going to talk about how it affects things like when I have a bubble, why I see light. So lights that are in phase get stronger, lights that are out of phase cancel each other. And so this has an effect when I have a thin film, like a bubble, or I see gasoline on the ground, and I either see a color or see a rainbow of colors or see nothing coming out of it. How thickness of this film affects, and the phase changing here affects that interference. I've now redrawn this example, and all I did was I flipped the order of the media. So I now made media 1 be the media that has the higher index of refraction, and media 2, the one that's going into, be the media of lower index of refraction. So for example, this is water or glass, and this would be air. So I do put water in there. So when I solve again the same way, so I have the same angle of incidence, I get some refraction, I get some reflection, and then I have some refraction into this new media. And so I'm going to solve for theta 2, and I can see that this theta 2, since N1 now is greater than N2, my theta 2 is going to be greater than theta 1. So it's the refracted one is moving away from the normal surface. And that can keep happening until I come to what's called the critical angle. And at the critical angle, I would, shown here by red, the incoming ray would hit this, and I would find out, I'd get a refracted element, which would be at 90, find theta 2 is 90 degrees. And that's the most I could ever do and have any energy go into media 2. If I go a tiny bit beyond there and I solve for, it'd say theta 2 is 91 degrees. And it'd say, but that would say 91 degrees relative to this would be something which would actually stay, not even go into media 2. So therefore it's an invalid solution. So the greatest I can ever have is theta 2 critical will be 90 degrees. So if I want to solve for that critical angle, then I'm going to put a theta 2 here of 90 degrees. Well, the sine of 90 degrees is 1. So I can solve for theta 1 then, as I've shown right here. So I'm going to solve for theta 1, and it's just going to be n2 over n1. So n2 over n1, and that only happens, and so you put the numbers in here, n2 1.003 over 1.33, and take the inverse sine of that, I get 48.773 degrees. So that's saying if I have an angle relative to the normal of 48.773 degrees coming in, I would get a theta 2 then of 90 degrees. And I can't ever, if I exceed that angle, if I go 48.774 degrees, then no refraction at all takes place. No energy goes into media number 2. The only thing that happens is I get all reflection. And so that's and now that only happens one way, because again, if I'm going the other way from a lower index of refraction to a higher one, when it bends to the center, there's no case where, I mean, I can always get that energy to go into the other media. So it's always in this one direction where I have a critical angle. And if I have any angle that exceeds that, then all the energy stays within this. So it's called total internal reflection, because no refraction takes place. So if I have an angle greater than theta 1 critical, there's no refraction and there's no energy transfer to media 2, because there's nothing reflected into it. And that's actually beneficial to us in this world. For example, if I have waves running down this way, for example, in a glass fiber optic cable, and the waves are transmitting energy, and on the walls if there's air, and that's going to hit, if it's going to hit this air on this, it's going to bounce off, hit this air, and it's going to be at such an angle greater than the critical angle that none of the energy goes the outside, and so it's just going to no refraction, just all reflection. So makes like fiber optic cables very efficient, because all the energy is staying internal because there's total internal reflection. Another thing it would be, for example, if I might be a kind of a test problem, if I'm a scuba diver and I kind of I'm in water and I shine my light at a shallow angle, if I shine straight out of the water, I'll see light ray coming out of the water. Someone in the air could see it. But if I shine it at an angle greater than the critical angle, then there'll be no refraction into the air. That light will all just bounce back and stay inside the water. And remember, that's only a one-way direction. I still could always shine at air. I can shine very shallow at air, and it would still refract into the water. Now let's take, like we did before, let's take a real close look at what happens right at that interface in the wavelength domain. So once again, I have an incident angle, I'll have some reflection, and then I'll have, as I show it, I have this refraction which is going away from the normal of the surface. Now let's think about velocity. I'm going to a lower index of refraction. So lower index of refraction gives me a higher velocity. So I'm going from a low velocity to a high velocity. Frequency stays the same in both the same media. And since I'm going at a higher velocity here, I'll get a greater wavelength. So I kind of do this as a shorter wavelength, and I go to a longer wavelength now. Also, as far as velocity goes, we know velocity of any electromagnetic wave is the ratio of the magnitude of the electric field compared to the magnetic field. And since I go to higher velocity here, I know in media 2 that ratio of electric field to magnetic field is going to be greater than it was in media 1. As far as the phasing, once again, I have a certain phasing here. I hit that the way I drew it. I'm at a peak when I hit that boundary. Now when I go to this other media, again, the phasing won't change with refraction. So it'll continue on the peak, continue from the peak and keep going down. Okay, keep the oscillation. What does change in this example relative to the previous one is what happens to the phasing of the reflected wave. In the previous one, I was seeing a 180-degree phase shift because N2, the media that I was going to, was greater than N1. And this time, the medium that I'm in is greater than the medium I'm going to, that I could potentially go to for refraction. So therefore, N2 is not greater than N1, and so therefore the reflected wave doesn't change phase. So I'm coming in and I have this phase, I hit the wall, I'm at the peak, I just continue on and I just keep going on, so it reflects off this and it maintains the phasing of it. And that's very beneficial. Again, back to our example of let's say I had this wave traveling down glass in my fiber optic media, and most of it just keeps going down and doesn't hit this wall, but there's going to be some that's going to be slightly off angle, or maybe the fiber optic is bent a little bit, and it's going to come and hit this interface between the glass and the air. And so the signal's moving down, and it's all moving down at that certain phase, and when it hits this air boundary, if it switched phase, then suddenly I'd have part of this signal would be out of phase, would be 180 degrees out of phase with the rest of the signal, and I'd start having, and then I'd have, every time I have reflection, I'd start having chaos downstream, because I'd have all this signals that some would be additive and some would be subtracting based on how much it reflected or not off this wall. But what happened? What the world's helping me is that when I am in glass and going to air, I don't have that phase shift. So on this reflected wave, so I'm coming down, I have a certain phasing. It can bounce off, it can reflect off that wall and maintain the phasing of everything else that was there. So this phasing, this signal just keeps stays uniform. Nothing gets 180 degrees out of phase. In that phasing relationship of, for example, a fiber optic cable that has total internal reflection helps to remember what happens at that boundary. So I know now that if I'm in a media that has a higher index of refraction than the other media at the boundary, that I will stay in phase. And the fact that when I think about fiber optic cables, it helps remember that when I, for example, in glass and at the boundary, other boundaries air, that I stay in phase, helps remember that relationship of the phasing, when it changes and when it doesn't change for reflection.